So we're going to look at an object in free fall, and we're going to assume that we have a 4-kilogram object, and we're going to be dropping it from a cliff. Now, first question here, it says describe the acceleration and velocity the instant the object is released, when it is halfway down the cliff, and the instant before it hits the ground. Well, now acceleration is constant. Okay, so the acceleration of the object in free fall never changes, and it is always the value of gravity. So our acceleration at every single one of these places is going to be negative 9.8. meters per second squared. Okay, because gravity does not change. When the object is halfway down, gravity is still pulling on it in the same fashion and accelerating it at negative 9.8 meters per second. Okay, now the velocity, though, on the other hand, that does change. So the instant the object is released, the velocity would be 0. So we're just saying that very instant when it's released, it hasn't started moving yet. So our velocity would be at 0 meters per second. When it's halfway down the cliff, we don't necessarily need to do any calculations, but we're going to just say that the object would be moving faster. Okay, and then the instant before it hits the ground, it's going to be at its highest speed possible. So it's highest speed possible. So what's going to essentially happen is because acceleration is always increasing the speed by negative 9.8 meters per second every second, that velocity or that speed is going to be increasing every instant as it falls. So it's going to be getting faster and faster and faster as it falls down the cliff. That is assuming that we don't reach terminal velocity. Now again, remember the negative on here is just indicating the direction that it's going downward. So just kind of keep that in mind. Now part B, this one is actually a computation one. What is the velocity 3 seconds after the object is released? So from our formula sheet, we have a formula that says our final velocity is equal to our initial velocity plus acceleration times time. Well, we're trying to find what is that final velocity. So we have VF is equal to, well, our initial velocity is 0 because when we release it, we didn't throw it downwards, we just dropped it. So our starting velocity would be 0. Our acceleration would be negative 9.8 meters per second squared. And then our time is 3 seconds. Okay, now the 0 doesn't do anything to our computation, so we need to take negative 9.8 times 3. And notice that I have seconds in the numerator here and I have seconds squared in the denominator, so it will cancel out one of them. My final label is just going to be meters per second, so I compute my final velocity to be negative 29.4 meters per second. But I need to go and check for significant figures, and I only get 1 from that 3 seconds, so I would write this as negative 30 meters per second would be my final velocity. Okay, now question C says, if it takes 4.5 seconds for the object to hit the ground, how tall is the cliff? Well, on our formula sheet, we have another formula dealing with distance, and that would correspond to how tall something is. What's the distance that it fell? So our formula says that D is equal to initial velocity times time plus 1/2 acceleration times time squared. So if we start plugging in the values that we know, my initial velocity from above I know is 0. My time is 4.5. Acceleration due to gravity is negative 9.8. And then my time again is 4.5, and that value is squared. So when I start solving this one out, 0 times 4.5 is 0. And when I take 1/2 times negative 9.8 times 4.5 squared, Now, only the 4.5 is squared. So you have to square the 4.5 only, and then times that by negative 9.8 and times it by the 1/2. That ends up giving me D is equal to negative 99.225 meters. Now, the reason that this is negative is because our formula calculates the distance that it has traveled, and the negative has indicated that it is traveling downwards. So the object traveled downwards negative 99.225 meters. The question, though, says how tall was the cliff? So when we would measure the height of something, we would give the positive value. So we would have 99.225 meters. And then again, check for significant figures. We get 2 in this one. So we would leave this at 99 meters tall is how tall our cliff is. Okay, so one of the main things to remember, though, in free fall is that the acceleration is always whatever gravity is, and your velocity is what is changing. The reason your velocity changes is because you have an acceleration. Okay, the next question was about centripetal force. So what is the centripetal force on a 2.1 kilogram rock that is being spun in a 2-meter diameter circle at 3 meters per second? Okay, well, our formula for centripetal force tells us, I think that we have it as the subscript force sub C is equal to mv squared divided by r. Okay, well, our mass is 2.1 kilograms. Okay, our velocity, the v, is 3 meters per second. Now that velocity needs to be squared. And then our radius, here's where you have to be careful. This says it's a 2-meter diameter. So diameter is all the way across the circle. We need radius, which is only halfway across the circle. So we only need half of this value. So our radius is 1 meter. Now if we look, no, let me get rid of this, hold on. Okay, so the first thing I would do is I would technically square my 3 meters per second, and I'm going to go ahead and do that and write it over top. So that would turn out to be 9 meters squared per second squared. I just want to show you how the labels work out here. Now I have a meter in the denominator and I have meters squared in the numerator up here. So that meter is going to cancel out with one of those meters up top there. So now when I multiply this out, I take 2.1 times 9 divided by 1, and I end up getting 18.9, and my label is a kilogram meter per second squared. Okay, and that is the same thing as a Newton. So just to show you how our labels do end up working out, it does work out to turn out to be in newtons. I do need to check for my significant figures, though. It looks like I only get 1. So I would have to round this to 20 newtons, or you could leave it as a kilogram meter per second squared. Either unit would be fine. So my centripetal force is 20 newtons. Okay, and then the last question for this one was dealing with potential energy. I also threw in kinetic energy and total energy in there. So our situation is we're going to have a 4-kilogram ball is held from a ladder that's 4 meters above the ground. Okay, so what is our potential energy? Well, our formula for potential energy says that we have to take the mass times the gravity times the height. So in this situation, we take our mass, 4 kilograms, times gravity. I'm going to go ahead and use 10 for this one, times our height, which is 4 meters. Okay. Multiply that all out, and you should get 160. And our label, we would have a kilogram. Now notice we have a meter times a meter, so that's a meter squared. And then we have a per second squared. Okay, and that gives us a kilogram meter squared per second squared. which is an acceptable unit for energy. So that would be our total potential energy. Let's check our significant figures. We only get 1, so I would actually need to round that to 200 kilogram meters squared per second squared. Okay, now question B says, what is the total energy? Well, when we are just holding this ball from the ladder, all of the energy is potential energy. So our total energy is also going to be 200 kilograms meters squared second squared, because those would be the same. There is no kinetic energy at that time that we have to worry about. It is stationary. It's being held. Now, question C says, once the ball is dropped and is halfway down, what is the potential energy, kinetic energy, and total energy? Well, our potential energy, if we look at our formula, the mass doesn't change, the gravity doesn't change, the height changes. So the height is 1/2 what it was before. So you could either, if you're more comfortable recomputing it, you could recompute it and take the 4 kilograms times gravity times 2 meters, because it's halfway down, so now it's only 2 meters above the ground, and you could compute it that way. Or if you recognize that half of h would then produce half of the potential energy, we could also just take half of the 200, and our potential energy would be 100 kilograms meters squared per second squared. Okay, now the kinetic energy and the total energy. Well, the law of conservation of energy tells us that energy can't be created or destroyed, so our total energy still has to be 200. That can't change. Well, if only 100 of it is potential energy and we need 200 total, that means the missing portion has to be in kinetic energy. So we don't actually have to use the kinetic energy formula with our 1/2 mv squared. We can just use the law of conservation of energy. I need 200 total, I only have 100, so that means my missing portion has to be 100, and that would all be in kinetic energy. Okay, now question D, the instant before the ball hits the ground, what is the potential energy, kinetic energy, and total energy? Okay, well at that instant, we are assuming the height to be 0, so our potential energy is 0. The total energy, again, cannot change. It has to be the same. So I know my total, again, is 200. The potential is 0, which means that all of the energy has transferred itself into kinetic energy, so there has to be 200 kilograms meters squared per second squared of kinetic energy now. Now I could then follow that up and ask you, so the instant before the ball hits the ground, what is its velocity? Now we could use the formula that kinetic energy is equal to 1/2 mv squared, and we could put in our 200 for the kinetic energy is equal to 1/2, our mass was 4, and then we can solve this for v squared. Okay, so to solve it, to get rid of the fraction, I would multiply both sides by 2 over 1. It's going to get a little scrunched down here. I'm going to get rid of this. Top here. So that would then give me 400 is equal to 4v squared. I could divide both sides then by 4 to get rid of that 4 over there and get 100 equals v squared. And then to get rid of this square, I would need to square root both sides, and I ended up getting a velocity of 10 meters per second. So I could then extend it to ask for the velocity if we did need to use that equation.